Hello everyone, my name is Fabio and I'm here with my friend Sheldon. And today we'll be explaining our research with the title Comparative Analysis of Transformation Consistency Detector and Latent Neighborhood Graph on a Simple Convolutional Neural Network for Adversarial Attack Detection in Image Classification.
Alright, so let's start with a question. What if I told you that an AI system, one that's been trained for months, tested thoroughly, and deployed in a real world security system, can be completely fooled by a tiny, invisible change to an image? Like, we are talking about pixel level, that you and I would never notice with our eyes. But the AI completely lose it and misclassify the input entirely. Sounds wild, right? But that's exactly what adversarial attacks do. And they are a very real, very serious problem in the world of machine learning security. Now, convolutional neural network or CNN are one of the most popular architecture for image classification. They are used in face recognition, medical imaging, autonomous vehicles, security cameras, and so on. But here's the problem. CNN are surprisingly fragile when it comes to adversarial inputs. Someone can take perfectly normal image, add a tiny calculated perturbation to it that is literally invisible to the human eye, and the CNN will confidently misclassify it. That that's something terrifying, right? When you think about the real world implication. So the question becomes, what do we do about it? The most obvious answer the most obvious answer is adversarial training. Basically, you retrain the model using adversarial example so it learns to handle them. Simple idea, right? Except it's computationally expensive. It takes a long time, and studies have shown it can actually hurt the model performance on clean, normal data. So that's not always a viable option. That's where attack detection comes in. Instead of trying to make the model tougher, what if we add a security layer before the model even processes the input? Something that checks whether the input has been tampered with. If it has, we flag it and stop it before it reaches the classifier. That's the whole premise of this research. And specifically, we are comparing two very different detection approaches to figure out which one is actually better and when and why. So, let's break down how it works exactly. Okay, our setup is a lightweight vanilla CNN. Nothing fancy, no defense mechanism baked in, trained on CFAR 10, which is a standard benchmark dataset with 10 image categories like cars, birds, cats, plant, and so on. We then attack the CNN using two of the most well-known adversarial attack methods out there. First is FGSM, fast gradient sign method. This is a one-step attack. It basically computes the gradient of the loss with respect to the input and nudges the image in the direction that maximizes the model's error. It's fast, it's simple, and it's effective. Think of it is a, think of it as a quick jab to the model. Second is PGD, projected gradient descent. This one is more like a full combo. It does multiple iterations of FGSM like steps. Each time staying within a defined perturbation budget. It's slower but significantly more powerful because it has more opportunities to find the optimal adversarial perturbation. PGD is widely considered one of the strongest first order attack available. Now, on top of these attacks, we place two detectors. The first one is TCD, Transformation Consistency Detector. The idea behind TCD is actually really intuitive. Take a clean image and transform it in minor ways. Crop it, pat it, and flip it. And feed its transformed version through the CNN. A normal image should produce consistent prediction across all those versions because the core visual content doesn't change. But an, an adversarial image, that tiny perturbation is fragile. When you transform the image, the perturbation gets disrupted and the model predictions start jumping around. That inconsistency is the signal. If the prediction vary too much, TC flag it as adversarial. The decision threshold is determined using validation data by comparing score distribution of clean and adversarial samples. The second, The second detector is LNG. And how LNG works? Sorry, before it, LNG is Latent Neighborhood Graph. This one is more sophisticated. Instead of looking at the model output prediction, LNG goes deeper. It looks at the internal feature representation of the input inside of the CNN. Specifically, it extracts the latent features, basically the CNN internal encoding of the image, and then checks how that encoding fits among its k nearest neighbors in the latent feature space. The idea is that clean input tend to have stable, well-structured neighborhood in the space, while adversarial inputs, even though they look visually similar, have distorted internal representation that don't fit naturally among clean samples. A graph is constructed from this neighborhood relationship, and then a graph convolutional network process that graph to make a final detection decision. Is it normal or adversarial? So the key difference is really about perspective. TCD what's what the model says. LNG what the model feels. In a sense, it's internal representation. And as we'll see in the result, this difference leads to very disparate behavior.
Okay, now, after we learn about how it works, I'll explain the results of the experiment. From our experiments, both the Transformation Consistency Detector or TCD and the Latent Neighborhood Graph or LNG were able to detect official examples generated using FGSM and PGD attacks on the CFAR10 dataset. Before applying any attacks, both CNN models performed quite well. The model using TCD achieved a clean accuracy of 79.65%, while the model using LNG achieved 80.69%. However, once adversarial attacks were applied, the performance dropped significantly. Under the FGSM attack, the accuracy decreased to only 4.21% for TCD and 3.93% for LNG. When using the stronger PGD attack, the accuracy became even lower, reaching only 1.01% for TCD and 1.34% for LNG. These results show that although CNN performs well on normal images, it is highly vulnerable to adversarial attacks. Next, let's look at the detection performance. LNG achieved a very high true positive rate, or TPR, with 89.59% for FGSM and 87.48% for PGD. This means it successfully detected both adversarial images. However, LNG also produced a very high false positive rate of 76.91%, meaning many clean images were incorrectly classified as adversarial. On the other hand, TCD showed the opposite behavior. It had much lower false positive rate of only 4.32%. So it was much better at preserving clean images, but its true positive rate was only 4.33%, and its F1 score was below 1%, meaning it missed most adversarial examples. So we can clearly see the trade-off between these two methods. LNG is much more sensitive in detecting attacks, while TCD is much more conservative and produces fewer false alarms. Okay, to conclude this research, we compared two adversarial attack detection methods, which are Transformation Consistency Detector and Latent Neighborhood Graph, on a CNN image classification model using the CFAR10 dataset. The experiments showed that both FGSM and PGD attacks greatly reduces CNN's classification accuracy. This confirms that CNN-based image classification systems are still highly vulnerable to adversarial attacks. From the comparison, as we can see, LNG achieved much higher detection sensitivity. It successfully detected more than 87% of adversarial examples for both attack types, showing that latent neighborhood graph techniques are effective for identifying adversarial perturbations. However, this high detection capability also causes a high false positive rate. meaning many normal images were mistakenly detected as adversarial. Meanwhile, TCD showed the opposite characteristic. It maintained a very low positive rate of around 4%. So, it was much better at recognizing clean images correctly. However, because of its low true positive rate and F1 score, it was not very effective at detecting adversarial examples under our experimental settings. Overall, LNG is better choice when detecting as many adversarial attacks as possible is the priority, while TCD is more suitable when reducing false alarms is more important. So, in conclusion, there is no single method that is best for every situation. The choice depends on the requirements of the application. That's it from us. Thank you.
Thank you.